Oh, can you hear me now? Cool.
Hi, it's Chaz Beichman here. Can you hear me?
Yeah, clear. Thank you. And by the way, so this defense is going to be live on YouTube. So finishing days. Okay. Oh, okay. Sure, sure, no problem. Thanks. Thank you. Oh, by the way, there are some refreshments outside if you can help yourself. Some fruits and cupcakes. Have about 4 or 5 minutes to go. There is a link live on YouTube. Can you check it for me if this is running? I sent it to the group in our lab. Thanks. Hi, Professor Allen. Nice to meet you. Thank you so much for being here. I know it's pretty early today. Okay, okay, I'll have some updates on the thesis as well, so I'll send it out. Thank you. I spent some time studying on that. I really want to have some time to discuss that with you, like what is orbital resonance, like how do you think that is related with the resonator? There's kind of similarity, yeah, but I'm trying to figure out like how is this, yeah. So, hello? Hello? Yeah, let's wait for Professor Marandi. No, yeah. Yeah. Hi, Professor Marandi. Nice to meet you. Thank you so much. Great, how are you? So here will be the microphone for you. Hello? Yeah. Thank you. Okay, so it's almost 9, so I'll get started. Do you want? No, not really, like because I ran a practice talk yesterday, so I guess the group members will not. Yeah. Charles, yeah. Yeah, he's on Zoom. Thank you. Okay, thanks everyone for being here, and thank you so much for great support. Uh, so yes, there are some refreshments outside if you want. Help yourself, and thank you for everyone being here. So the fourth committee member will be online. Charles, thank you for being here. And the title today will be physics applications of compact optical frequency comb. And here I placed 2 photos in a cover image, and which each photo represents one of the project I will be focusing on today. And although I put the 2 photos together, like they do not share the same scale bar. Okay, so the left-hand side you have the observatory, like which is I'm going to demonstrate a application of the compact optical frequency comb which is called electro-optic frequency comb, and how that kind of comb can be used in astronomical calibration. And on the right-hand side, you can see this is a demonstration of another kind of compact optical frequency comb, or sometimes people also call it integrated frequency comb. And this is specific device, we have like multiple resonators that are coupled together. And you also can see that the spectrum is emitting from this device is very colorful. So hopefully after the second part of my defense, you will have a good idea on like why those multi-resonator coupling is necessary and why this optical spectrum output is very colorful. So let's get started. So as this image indicates, like this defense will be mainly separated into two parts. And the first part, I will be discussing the exoplanet searching using the electro-optics frequency comb, which is kind of a compact optical frequency comb. And the second part, I will be discussing the generation of a new important kind of optical frequency comb, which is we call them bright soliton, and how this is possible in a kind of platform which were traditionally considered to be very challenging to generate this kind of bright soliton frequency comb. So let's get started with a brief introduction on what is the optical frequency comb for general audiences. So the optical frequency comb, as the name indicates, is a series of frequency lines in the spectrum domain. And the spacing between those individual lines are the same. It's similar to the teeth of the comb. And if all the faces of those comb lines are the same with each other, in time domain, this optical frequency comb can form a periodic pulse train. And how is a kind of optical frequency comb is so important for modern photonics and the optics engineering? So one reason is that the optical frequency comb is serving as the bridge between the electronic frequencies and the optical frequencies. So how do we understand this claim? Because the optical frequency comb is a frequency comb that's located in the optical domain, which has a carrier frequency and the optical frequency roughly about a few hundred terahertz. And if you talk about visible, it's even higher. And the spacing between the adjacent comb lines are typically on the level of megahertz to gigahertz. And these frequencies are typically on the, we consider them on the level of electronic processing bandwidth. So with the optical frequency comb, we are kind of linking them together with linking the optical frequency and the electronic frequency using this component as a specific mediator. And why linking them together is so important? Because like one reason we can argue is that using this link, we can somehow transfer the well-established techniques in both optical frequency domain and electronic frequency domain on stabilizing the frequencies. Like for example, there are a lot of well-established techniques which we can use to stabilize frequencies for lasers. And if you adapt those techniques with some other tricks, and you can down convert those. For example, you can take the bit node between the comb lines of this optical frequency comb. You can somehow down convert this reliability or stability in the optical domain to the radio frequency domain. And this process called optical frequency division. And from the other side, from radio frequency to the optical frequency, like we have a lot of very low phase noise and reliable radio frequency sources right now that are commercially available on the market. And you can take the advantage of those devices and, for example, take the radio frequency source as a modulation driving signal, and you can drive the single frequency laser, and you can generate a arbitrary, or we call it electro-optic frequency comb, which I'll be discussing in the first part of my thesis defense. So I think this argument somehow validates that like comb is a very critical component for the optics and frequency engineering, and this was awarded half of the Nobel Prize in 2005. So I will get started with a few applications of this. So other than the few applications I just mentioned, other applications, for example, you can use optical frequency comb for spectroscopy, which adapts a similar idea that you are linking the information that were stored in the optical domain down to the radio frequency domain using an optical frequency comb as a mediator. And another very interesting and exciting application of the Doppler frequency comb is how we can utilize this Doppler frequency comb for exoplanet searching as a frequency calibration in astronomy observation. So I will start with this application first, and talk about the first project and going to the first part of my defense today. So the observatory I was really honored to work with was the WMCAC observatory located in Hawaii, and you can see that this observatory have two individual domes, and each dome is hosting a 10-meter diameter reflecting telescope. And to give you an idea on like how big is this 10-meter telescope right now, I listed some of the few of the biggest existing reflecting telescope right now in the world. And you can see the CAC-1, the two CAC reflecting telescope is among the few biggest reflecting telescope right now existing in the world now. So it's my great honor to be able to work with them. And one of the important scientific tasks for the CAC observatory is to do exoplanet searching. So let's get started with explanation on what is exoplanet and why like searching the exoplanet is important and difficult. So exoplanet, as an analogy, imagine that you are an alien living outside the solar system, and the sun and Earth. You can sun Earth is Earth's two body system. The Earth in your view will be the exoplanet. So what is happening that you want to observe the Earth by looking at the sun, which is kind of difficult because the Earth itself is not emitting any light. So you cannot really identify the Earth by directly looking at any light as emitting from the sun, from the sky, right? So what you can do is that you can only observe the sun, what's happening with the light emitting from the sun, and can identify, okay, there is a exoplanet that is rotating around this hosting star. So how is this possible? So one way we can do this is we call this the radial velocity Doppler spectroscopy. So because like probably everyone knows about this, the two-body system is not actually, the center hosting star is not actually stationary. It is doing an effective two-body motion around the center of mass between this system. And because of this effective rotation motion of the hosting star, and if you look at this motion from the radial side, from the radial direction, you will be able to see that this hosting star is periodically moving towards you and away from you. And because of this periodic motion, you can identify this periodic motion by monitoring the frequency that is emitting from this hosting star, because like the frequency you observe from this hosting star will have a Doppler shift due to this periodically changing radial velocity. So this process is called Doppler spectroscopy, and here's an example of the identified exoplanet using this method. So this vertical axis, you can understand it as the frequency you observed, which you can correlate with the radial velocity as well. So you can see the velocity is periodically changing on the level of years, and you can identify this frequency periodic change. And then you can confirm there is an exoplanet rotating around this hosting star you're observing. One important critical factor on like how precise you can do with this Doppler spectroscopy will be the frequency resolution. So why this frequency resolution is so important? Let's do a quick calculation. Like take the formula of Doppler shift of light and take a quick derivation. You can get the relative resolution of the radial velocity as a fraction of speed of light. It's actually proportional to the relative resolution of the frequency that you can observe. Yeah. Where? Yeah, this is also dimensionless. This is speed. This is speed of light. Yeah, yeah, velocity. Yeah, this is also yeah. Uh-huh. then you can only identify the radial velocity. Yeah. Right. It, yes, exactly. Yeah, so that's correct. So we can only identify the radial velocity using this method. If it's like the bad luck, it's not rotating around the radial side, it's gonna hard using this method. So going into this quick derivation, you can see that we really need to boost our resolution in the frequency domain. And if you are familiar with the languages in the optics, this number is actually typically characterized by the Allen deviation of the frequency. So the Allen deviation will be pretty important factor we'll be discussing later. So to give you another idea on like why radial velocity spectroscopy is so important in the exoplanet searching, here I plotted a statistic of the exoplanets that are confirmed using different methods. And these two plots are up to date this Tuesday. So I get the data from an open source exoplanet searching database. And up to date on Tuesday, like there were total of 5,488 exoplanets already confirmed. And among all those confirmed exoplanets, like roughly about 20% of them are confirmed using this radial velocity technique. And another very important reason, like why radial velocity technique is so important, is because I'm not a true expert on this, but as a matter of fact, I know like the radial velocity and the astrometry are the only two methods that can help you to identify the mass of the exoplanet. And astrometry cannot be done on the ground. So the only radial velocity method can be done on the ground and can use this method to identify the mass of the exoplanet. So this will be pretty important if you want to confirm whether the exoplanet you are looking at is a rocky planet or not, because you need the mass information to calculate the density, right? And also you need to combine it with some other information you get from other methods, for example, transit methods. So, given such importance of the radial velocity method, we need to develop some technique to boost the frequency calibration precision. And here is some motivation on like why we need to boost this frequency resolution motivation. So for example, if you consider yourself as an alien outside of solar system and you are trying to identify the Earth rotating around the sun, what will be the precision needed for that kind of observation? This will be easily calculated by you can calculate the effective two-body motion between the Earth and the sun, and the radial velocity of the sun will be around like 9 centimeters per second. And the current precision, like using the calibration from the telescope, for example, there are very advanced telescope. It's called a Keck Planet Finder. That precision is on the level of 30 centimeters per second, and it can be better, I believe, like with recent developments. And if you calculate those stabilities as a fraction of speed of light, it's about 10 to the minus 9. So this is about 10 to the minus 9. So we really want to boost this even further. With the laser frequency comb, like we can achieve the precision like about 10. At least we think that we can achieve the precision up to like 10 centimeters per second. And another like reason is that this frequency comb kind of works very well in the near IR spectrum. And with this near IR reference, it's kind of helpful for you to identify some other planets which is rotating around the cooler sun, a cooler star. So that's another kind of motivation for us to develop a comb that is spanning between the wavelengths from like 1200 to around like 2100. Yeah. Yeah, that is the referencing you have for the laser frequencies. Like for example, I will go through more detail on what we are referencing to. Like currently, what we are referencing is a hydrogen cyanide. Excuse me. Currently, what we are referring to is a rubidium cell. And previously, like in Bo Qiang's previous work, he was referring to a hydrogen cyanide. So these are all like atomic or molecular transitions, which are kind of have a limit if you don't do too much engineering on this. Exactly. Exactly. If we do a full self-reference comb, it'll be much better. And that will be a further development, probably in the next step for high spec. And the final goal is that we want to push the stability the laser frequency comb can achieve up to like 1 centimeter per second. That will be the ultimate goal. And why laser frequency comb and electro-optic frequency comb is so important in this kind of application. Another reason is that people may ask, like, why you don't use a well-developed commercialized fiber laser comb? One reason is that the fiber laser comb usually have a repetition rate on the level of few hundred megahertz. And if you inject this kind of frequency comb into the spectrometer you have, the spectrometer really cannot resolve this line spacings. In other words, like you are absorbing the envelope instead of the individual comb lines if you have this kind of very, very low repetition rates. So if you really want to use fiber laser comb, you need to do some other engineering. For example, you need to do spectrum filtering with the filter cavities, and those will include some other technical issues which may not be very reliable. But that exists. I would need to acknowledge. So there are some advantage with our laser frequency comb, which we naturally have a repetition rate on the level of 16 gigahertz in our specific case, which is pretty suitable for the telescope resolution they already have. Okay, so as a conclusion of this slide, so what we are doing, like if you think back on the animation we started with, we claim that the optical frequency comb is kind of a link or bridge between the optical frequency and the electronic frequency. And what we're doing now is that we are taking the radio frequency source, which has a very low phase noise, very reliable. We're taking that source as a driving source that can modulate or phase modulate a single frequency laser so that you can generate a optical frequency comb, or we call it electro-optic frequency comb. Using this process of where we are up converting our stability or reliability on the radio frequency domain to the optical frequency domain. So, and this process kind of we call optical frequency synthesizing. And the generated optical frequency comb has a bandwidth of about this first step, or the first stage, or we call the seed laser pulse of this electro optical comb is about 12 at most 15 nanometer in the bandwidth. So this is far from enough. You have questions? Mm-hmm. Your offset frequency is locked to a atomic. Yeah. Yes. Yes. There's a pretty big difference. Yeah. It's a pretty big difference. Yeah. And yeah. So let's continue to move on. So here are some. I'm not going into too much detail on like what are each individual components within this electro-optic frequency comb, and just a high level review. Like you have a continuous wave laser as a starting point, and this continuous wave laser goes through multiple stages of phase modulation and intensity modulation, and finally with some phase compensation, you can get a periodic pulse train with a bandwidth of about 12 nanometer in the frequency domain. And this 12 nanometer bandwidth is definitely far from useful for astronomers because like they care about a much broader bandwidth. So what we have to do is that we have to send this seed laser through multiple like post broadening stages. Like in our case, like we start with this electro-optic frequency comb, and we send it through like the two consecutive broadening stages. The first broadening stage will be the high nonlinear fiber. And after this, like the comb will have a bandwidth for about 200, 300 nanometers. And you send it further through the high nonlinear Tantalum waveguide. And this waveguide is pretty powerful. If the input pulse has the right condition, for example, they require us to have a short enough pulse and strong enough pulse energy. With those critical conditions already met, you can get even optically the octave frequency comb from the pulse they are sending in. In our case, like in our case, we can confirm the comb can span from 1300 nanometer to 2100 nanometer in the lab. So here is the comb spectrum we taken in the lab, and here is the comb spectrum we measured on the mountain. And excuse me, like this is like only a screenshot because like this is a data we get from another piece of equipment. And we can identify the candidates ranging, spanning up to about 2100. And here are some exposure. Yeah. Here? Yeah, I see. No. This is what we intentionally did this with a flattener. Yeah. It's effectively a wave shaper. It's a spatial light modulator actually. Yeah. So, but similar to a wave shaper. So this is with the flat spectrum is more favorable for astronomers because they can have a kind of like stable intensity or photon counts along their yeah. Yeah, that's okay. I would say like I haven't personally been able to use a real broadener made from silicon nitride, but this product I'm pretty happy with that. Like this product, the requirements is roughly I believe that you can request the data sheet from the company that's providing this, and the pulse energy requires about 200 picojoule per pulse. If you calculate the 200 picojoule per pulse with the repetition rate on level of 16 gigahertz, it's roughly about 3.5 to 4 watt. If you count also some like loss on the signal chain, and the pulse width requires about 100 femtosecond to 200 femtosecond, and for 100 and 200 femtosecond, it's pretty achievable with the nonlinear fiber broadening stage. So. But yeah, definitely, like there need to be some careful design on the nonlinear broadening stage because you need to do a careful phase compensation after the nonlinearity, and yeah, that involves a lot of work. But yeah, anyway, we can achieve this kind of broadening from 1300 to 2100 nanometers. And here is a exposure example, which we take from the spectrometer called NearSpec. And you can see this beautiful like series of comb lines illuminating the near spec pixels, and also the photon count with a clean series of comb peaks. And notably, like just 2 months ago, like April 26th this year, like this is the first time when the laser frequency comb and the starlight are simultaneously injected into the near spec. So this is thanks to the development of another critical component called KPIC. This is possible for now, and people can really like observe starlights and laser frequency comb simultaneously, which really makes the laser frequency comb more useful because like previously, what people are doing are they are first injecting starlight and then injecting the laser frequency comb as a calibration, and they're switching between them. Sometimes they only do 2 exposures over a night for laser frequency comb. So if you can really inject them together, this is going to be really helpful. And here's some further discussion on the island deviation I just mentioned about. So here we can, in the lab, we can achieve island deviation on the level of 10 to the minus 9. And if you calculate this as a fraction of speed of light, it's on the level of 10 to 30 centimeter per second. So which is the stability we just said that we believe we can reach to. Okay, so here we are going to conclude the first part of my thesis defense. With some nice photos, and I really appreciate everyone have been working with me, including all the tech staffs help a lot. And Dr. Stephanie, who unfortunately is not here, but really thank without her, like this project is not going to be possible at all. And this project was launched roughly about 2 years ago, and the first deployment trip happened last year on July. And the first, it had been running since November 2023, and the first on-sky observation just happened 2 months ago, like about April 2024. So this story is continuing, and there will be further developments and further improvements of this system. And another highlight is that I developed a full system controlling software, and which is available publicly available open source online. Okay, so as a finale and the starting point of the next part, let's come back to like why we claim this as a compact frequency comb and how compact it is. So here's a photo of the system on the left hand side, on the left bottom side. This is a photo of the laser frequency comb we developed for the observatory. And like you can see that even though we claim it is a compact sort of optical frequency comb, it is not really a very satisfying compact because it also involves a full equipment rack and also involves a half of the optical table. So the final dream, final goal of the photonic engineers are like we want to integrate the optical frequency comb in your phone size in the future, right? So this is not far from satisfactory. So we need to push this size further down, and the idea to do this will be through the integrated photonics, or we call them integrated optical frequency combs. So that will be the focus of my next part, or second part of my presentation. And to start with, we'll start with a brief introduction on the one critical component of the integrated frequency comb, which is the optical resonator. An optical resonator with high qualities has been intensively studied for a few decades. And those resonators are where the story started from. So the crystalline resonator and the resonator based on silica wedge. And those resonators can have a quality factor or have a quality very high. And in the language of the photonic engineers, we always refer to quality with a factor called Q factors. So later, whenever I mention Q factors or quality, they basically have this almost the same meaning. So, so the Q factor or quality of those resonators can feature on the level from a state of art from a billion to a few hundred billions based on whatever material you are working with. One drawback of those devices is that some of those devices are integrable, but they are not so integratable, which limits the high yield application or high yield production of those integrated photon devices. And this motivation drives people to further study on other materials which can be better integrated. And this list is far from complete, but just with some typical examples. But one common characteristic is that all those devices feature a lower, at least one order of magnitude lower quality factor comparing to the resonators where people started with. However, the Q factor doesn't beat the integratable goal for the engineers. So right now, like people really focusing on those kind of integratable high quality resonators, especially silicon nitride. And I will discuss like why this attracts so much attention for now. So quality factor, as you can see, this is a very important factor I have been emphasizing for a long time. So why this is so important, and why resonator is important in general. And this is a very well-known animation, probably everyone used in their presentation, which explains like when you launch optical field through the optical waveguide, which is coupling into the resonator, the optical energy can be built up within the resonator. And this optical energy build-up will enable the nonlinear optical process happening in the medium. And the nonlinear optical process are the process which can help you to generate a frequency comb from a continuous wave laser input. So probably as a general knowledge, probably you know about the nonlinear optical process. The strength of the nonlinear optical process is proportional to the intensity of the light. So you want to calculate like what will be the intensity you can have by doing this, launching the optical power into the waveguide, and do a quick calculation, taking some parameters that are pretty typical in our lab. The Q factor about 200 million, and the mode volume with the resonator on the with a diameter of about 3 millimeter. This is probably not too typical, but yeah, anyway. The intensity we can calculate that is circulating around the resonator is about 10 megawatt per centimeter squared. And this probably is not very intuitive, but if you compare it with another number, for example, you imagine yourself are going into a beach in a very sunny day and enjoying your sunshine. So what will be the solar flux density you feel on your skin that the solar flux density coming from the sun? So this number is about 100 milliwatt per centimeter squared, and this is about 8 orders of magnitude difference between each other. So kind of give you the idea like why this circulating power, circulating intensity within the resonator is so important for nonlinear optics applications. Okay, so given the fact that Q factor is so important, I can see that from this equation, the intensity itself is proportional to the quality factor. And with a higher quality factor, you can get a higher intensity, which will be favorable for the applications in nonlinear photonics. And also, for other nonlinear optic processes, they will probably involve like multiple photons that are interacting with each other. In those cases, some critical parameters may be even proportional to the second order or third order cubic, square or cubic of the resonator Q factor. So Q factor is really an important factor that we care about in the applications of the high quality resonators. So here's another project I did roughly about 2 years ago. I'm not going to go into too much detail about this project today, but I just give you a rough idea on like what is happening here. So the Q factors contains like mainly about 2 parts. We will be mainly focusing about only the intrinsic part today. And the intrinsic quality factor or the intrinsic loss channels contains multiple loss channels, including the absorption loss, which are transferring the optical energy into the heat and then further into the temperature. And another loss channel is the scattering loss, which is related with the surface roughness, for example, of the resonator. And those loss channels are pretty distinct from each other because the absorption of the material kind of pose a fundamental limit on what will be the highest intrinsic Q factor you can get by using this material as the material you're fabricating the micro resonator. So this kind of motivated us to isolate or characterize how much absorption you have for the photonic materials you are using from all the other messy loss channels you may encounter with. And so here are some technical details which I will not talk about today, but let me go through this very quickly and look at the result. So luckily, the method we proposed can characterize the absorption loss channel, and another very critical parameter is called the nonlinearity of the material taken simultaneously. So in this paper, we reported the characterized absorption Q factor and the nonlinearity factor of 4 materials together. And if you plot the result for these 4 materials in this figure, you can see they kind of follows a trend. And you take more think about this. Like when you are doing the photonic integration, what kind of material you really want to use? What kind of material property you want to have for the photonic material you are using? For the photonic material you are using, you want it definitely to have a higher absorption Q factor, which means that you want your material limited Q factor to be as high as possible, which means that you want the material to land as this region, right? With a higher absorption Q factor. And on the other hand, like you want your material to have a higher nonlinearity so that you have a better nonlinear optical process, which is critical for optical frequency comb, any nonlinear process in the photonics engineering. So you want your nonlinearity to be high here. So ideally, you want the material to land somewhere here. But however, the real life is not so ideal all the time. It's a typical trade-off between the nonlinearity and the absorption. For example, the widely used kind of material called silicon dioxide, silica. This material right now is widely used for cladding material. One main reason would be this low loss, and also for its lower refractive index as well. And another extreme example is the aluminum gadolinium arsenide, which is a semiconductor material. And semiconductor material typically is well known for its high nonlinearity. However, the absorption performance of the aluminum gadolinium arsenide, especially in this case, is like about 3 orders of magnitude worse than the silica we presented here. So it kind of makes sense if you look at this figure closely, why people finally land at the silicon nitride as a solution or widely used solution for CMOS compatible integrated photonic engineering. Okay, cool. Yeah, so Carrie raised a question on like what is governing this trend, or what is governing this trade-off between each other. Intuitively, answer would be you think about the band gap of a material. So with a rule called Miller's rule, if you have a larger band gap, typically you will have I forget smaller nonlinearity, right? A larger band gap you have a smaller nonlinearity, and with a larger band gap because it's hard for you to transit the electrons between bands, typically you will have a lower loss. So in this case, like the band gap is kind of governing the backhand physical principle that is governing this kind of trade-off. And this rule is like reported by other scientists called Miller's rule, which was observed about like 1962, a very very long time ago. So I hope this is a satisfactory answer to your question. Yeah. Yes. Yes. Okay. Uh,
Yeah, excuse me, Maodong, this is Chaz. Can you hear me?
yes, I can hear you. Thank you.
If I look at this figure, I
Uh-huh.
know it's in the near infrared. Um,
Uh-huh. Yeah.
one of the things we're interested in is performance down at shorter wavelengths. Is
Oh,
the
yeah.
same sort of data available, let's say 500 nanometers, and what would it look like? I assume the nonlinearity goes down a lot.
Uh, I don't believe we have data for 500 nanometer. That is
Or, some shorter wavelength at least.
close to yeah. Charles asked a question on like this data is shown in the communication C-band 1550. Do we have any data or any intuitive on this trend when we go to a shorter wavelengths? Like for example, 900, 500, you said? Even if I don't have the data, like I would be expecting this trend is kind of similar, and that's a guess. That is not responsible to draw that conclusion. And yeah, yes, subject knowing the band X. And another comment to Charles' question, we don't have data for for the wavelengths that are short to the visible. That probably is a little bit hard for experiment. But we do have some data at 1380. 1380 is close to the absorption peak of the hydrogen oxygen chemical bond or OH bond. And at those wavelengths, we can there are some experiments we can show that there is a strong peak or strong absorption peak of silica, which kind of helps you to understand like what is contributing to this absorption loss by looking at the absorption loss at 1380, which is close to OH absorption. So in that paper, like we kind of concluded that the OH absorption is a dominator in the current silica devices in the photonic engineering we are using. So yeah, and that is Appendix D in my thesis as well. So yeah, Charles, hopefully this gives you a good answer.
Yeah, thank you.
Thank you so much for that. Okay. So a disclaimer, like this is third order nonlinearity. Like we are not talking about anything related with OPOs or second order nonlinearity. Okay, so this is third order Kerr nonlinearity, and let's go into some details about the silicon nitride. And the silicon nitride is such a popular material, and there are multiple kinds of platforms that use silicon nitride as the waveguide material. One example is the high confinement silicon nitride. Conversely, there's a kind of material called low confinement silicon nitride. I will discuss it later, but it starts from high confinement. So what is called why is it called high confinement nitride? Because the thickness of the waveguide that you'll be using in this kind of platform will be comparable with the wavelengths you're operating at. And in this case, like the example is that we are operating at about 1.5 micron, and the thickness is about 1 micron. So because the thickness is comparable with your wavelengths, the mode is actually highly confined within the silicon nitride region. And that is the reason why this this platform is called a high confinement silicon nitride. And the Q factor fabricated from this platform can reach as high as 60 million, demonstrated by Giata's group, I believe. So one important advantage of this device is its dispersion. So why dispersion is so important? Because there is a exotic kind of optical frequency comb called optical soliton frequency comb, which can be generated with the anonymous dispersion. So let's start with like, what is the optical soliton frequency comb? So optical solitons are optical pulses. So if you see here, we have the optical pulses here traveling around the soliton, the microresonator. So soliton microcomb is this kind of optical pulses whose dispersion and the nonlinearity can balance each other so that this pulse will not disperse when it is propagating along the medium. This kind of feature is non-trivial because typically you think about the optical pulse that is propagating within the medium. This pulse, at least in time domain, it will be broader and broader because like different frequency components will have different traveling speed, right? But optical soliton case, this dispersion is actually balanced by the Kerr nonlinearity, so that this pulse will not disperse at all while it's propagating, and this is why it's called optical soliton. However, there's an important property of this optical soliton is that Kerr nonlinearity can only balance one type of group velocity dispersion, which is we call anonymous dispersion. So here is an analogy of what is anonymous dispersion. If you imagine that you are shining a white light into a prism, and this prism is going to disperse your white light into the colorful rainbow from red to blue. This is a pretty typical way you think about dispersion, and this kind of typical way we call this normal dispersion. And conversely, like if you think you're shining a white light into a prism and the prism disperses your colorful lights from blue to red instead of from red to blue, this will be anonymous dispersion. This is not very accurate because like what I said is on its phase velocity, but the actual definition of the dispersion is group velocity. But kind of give you an idea on like why dispersion is playing a critical role in those kind of applications. So as I just emphasized, only anonymous dispersion can be compensated by the Kerr nonlinearity. And luckily, like this high confinement silicon nitride features this kind of anonymous dispersion. So in the language of optical resonator community, we typically characterize the dispersion with the figure called integrated dispersion. And I don't have time now to explain what is integrated dispersion, but for your understanding and for the audience to understand the next part of my presentation, we only need to remember is that the positive curvature here in the integrated dispersion plot is what we want. So you can see here in the integrated dispersion plot of this high confinement silicon nitride, this features a positive curvature or is concave down. It features this positive curvature indicates that this is anonymous dispersion, and this anonymous dispersion is good, or in other words, like positive curvature is what we want. So you want this, you want to have this, and you can generate optical soliton by pumping at the position where you feature this anonymous dispersion. And the spectrum of the optical soliton, a typical spectrum is shown here. And this spectrum features a hyperbolic second square envelope. And this hyperbolic second square envelope is also is a property of the optical solitons we'll be studying later. So yeah, just in this figure, just remember positive curvature is what we want. So let's move on. Like there's on the contrast with the high confinement case, there's another type of silicon nitride platform which we call low confinement or ultra low loss silicon nitride resonators. And those resonators are fabricated with, of course, silica substrate and a thin layer of silicon nitride. This thin layer of silicon nitride we use is on the level of 100 nanometer. This 100 nanometer is like 1 order of magnitude smaller than the wavelengths we are using. Because of this, the mode profile that is traveling along this waveguide is actually scattering or distributing away from the central waveguide. It's also the distribution is also scattered around the silica region. And taking the advantage of the high quality of the silica I just discussed about you because silica has a very high absorption limited Q factor. So you will be able to generate to get a higher Q factor by using this kind of low confinement structure because like there are many optical modes that are distributing in the silica, which has a lower loss region. And the state-of-the-art Q factor can be achieved using this kind of platform, can be as high as 700 million. which is about 10 times higher than the high confinement case. And so the high quality factor is important for photonic integration applications. However, there's an important drawback of this device is that the dispersion is not favorable for us. So here's the integrated dispersion profile we show you here. The integrated dispersion for those resonators with high confinement structure are always normal. Or you can see this is a negative curvature in the integrated dispersion plot. And if we think about it more at the communication C-band or 1550, the thickness we are working with is about 100 nanometer. And this thickness is far from the thickness where we can reach anomalous dispersion. From this figure, you can see. This thickness is required to reach anomalous dispersion around about 600, 700 nanometer. So if you reach that thickness, it will kill your Q factor. And so we want to kind of somehow address this concern or make anomalous dispersion given this difficulty. And because like with this kind of dispersion, it is impossible for you to generate soliton directly from this kind of dispersion. So in order to address this concern, oh yeah, by the way, so I'm sorry, I forgot. So why this, another reason why this kind of platform is favorable because the fabrication process of high confinement or low confinement or ultra low loss silicon nitride is CMOS compatible. So in other words, like if you want to get a device fabricated from the ultra low loss silicon nitride, what you'll be doing is that you will do your design, draw your layout, send it out to the foundry, hit the bill, and wait. So you will not need to go into the clean room by yourself, and this is kind of another reason like why this is so popular now. Okay, so let's come back to dispersion. So dispersion here is normal, so we want to do something with dispersion, so we need to do something with dispersion engineering. And some of the dispersion engineering we can think techniques we can think about in this platform involves concentric ring coupling, polarization mode coupling, spatial mode splitting, and selective mode splitting. So all those four methods, say the method of concentric coupling, polarization coupling, and spatial mode coupling involves the coupling between different transverse modes. And the selective mode splitting involves the coupling between different longitudinal modes. So whatever, those dispersion engineering techniques all involve the coupling between different modes. So like why like involving coupling between different modes can help you to do the dispersion engineering. I will discuss that next. And in our experiment, we are adapting a very similar idea of this concentric coupling ring. However, we are also operating at a very different regime from this concentric coupling case. Because we are operating very similarly, so I will start from the concentric coupling case. So in the concentric coupling between two resonators, here I demonstrated here, the two resonators are fully coupled together, and the two resonators coupled together will have we assign them with a slightly different phase spectral ranges, so that in other words, they have a slightly different length of circumstance. Because of their slightly different phase spectral ranges, their integrated dispersion, which is represented by the two dashed lines here, are kind of off by each other by a little bit. And these two resonators can be strongly coupled with each other when the resonators have matched resonant modes have matched frequency and also matched momentum, which means that mode number matching, when the mode number match happens and also the frequency match happens, the two resonators can couple together. And you can see that when the two resonators are coupled together, you will generate like mode hybridization. And the hybridized or new eigenmodes will have like different dispersion comparing to the original dispersion you have. So in this case, like you have this well-known behavior called bandgap opening in physics sometimes. And the open bandgap, the upper branch of this open bandgap, you can see the locally here will feature some positive curvature. And if you play something with this local place with positive curvature, it's possible for you to generate anomalous optical soliton, which can only be supported by the anomalous dispersion, right? So this is the basic idea of the concentric coupling, and like hopefully this gives you an idea on why coupling between two resonators modes are important, and because the mode hybridization can modify the dispersion profile, and this modification can help you generate anomalous dispersion, and pumping at the anomalous dispersion can help you to generate soliton optical frequency pool. Okay, so we are operating at a very different regime. So what we are doing is instead of coupling them, fully coupling them, what we are doing is that we are partially coupling them together. In other words, the coupling region only involves a fraction of their circumstance. So in this case, because they're partially coupled together, and also the two resonators have like slightly different free spectral ranges. Because of this special coupling between the two resonators, the coupling will no longer require the mode number to be matched with each other. So in other words, the two resonators can be coupled together whenever the frequencies of the resonator modes are matched with each other. For example, at this point, this point, at this point, and at this point, at this point. So whenever the frequencies of the resonators are matched with each other, they will be able to couple with each other. And I will discuss more like why this coupling doesn't require mode number matching later. However, now let's look at this generated new dispersion profile, which is represented by the yellow curve. So different from the red, the green curve we're representing here, the yellow curve will have multiple band gap opening, and also as a result, multiple anomalous dispersion region where we can observe. And also this dispersion profile will have a spectral recurrence, and this spectral recurrence is set by the slope difference, right? The slope difference is the free spectral range difference between the two resonators. So here is a brief introduction on what we are doing, and let's dive into the most important results first, and come back to some technical details later. So here is the device we are using. So this device involves two partially coupled resonators fabricated with the ultra low loss silicon nitride, and the free spectral ranges of the two resonators are about 0.5% different from each other. They are both around 20 gigahertz. Because they are partially coupled together, the dispersion is modified, and generating an anomalous dispersion region is possible. So by pumping at the anomalous dispersion region, I just explain why we have pumping at this position. You can possibly generate a optical soliton comb, and if you look at the two resonators individually, this mode-locked soliton optical comb is traveling in a toss pair behavior. This toss pair is traveling around each individual resonator in a mirror shape, as demonstrated in this animation. So take a closer look at this spectrum. You can see this spectrum also features the well-known hyperbolic second squared envelope, and we need to further identify like whether this comb is coherent. So in other words, whether the faces of each individual comb lines are the same with each other. So in order to do that, we take the radio frequency bit note between the different comb lines, and in the bit note signal we identify a clear, strong single tone radio frequency signal, which indicates that this frequency comb is indeed coherent, or indeed it is a pulse in the time domain. And this time domain coherence is also confirmed by doing the autocorrelation, time domain autocorrelation here. Another feature of this spectrum is you can see there are two strong sidebands here. And I will discuss another project related with this sideband later. But now let's see why this sideband can happen. A quick argument or quick explanation is that you look at the integrated dispersion curve we plot together with this spectrum. And the integrated dispersion at the position where the sideband can be observed is almost the same with the position where you are pumping with this soliton. So in other words, this dispersive wave or strong sideband can be observed when the integrated dispersion is roughly the same with where you are pumping with it. So we will come back with dispersion later, and let's come to some technical details on how this dispersion is achieved. So let's remember, like this dispersion have a M-shaped curve, and remember this M-shaped curve we will jump out soon. So this M curve shape is actually a zoom in of this local region. So you can see there is a very shallow positive curvature here, and that M curve was a zoom in of this region here. So if you can take a look at this dispersion profile, you can see that this overall it features a negative curvature, or in other words, it's a normal dispersion. However, like we are coupling this, the coupling resonator will create like two sets of eigenmodes, and one set of the eigenmode around this region will have the anomalous dispersion, which is where we are pumping at. And also, as I discussed earlier, because we are partially coupling together, the coupling does not require mode number matching. so that this coupling can happen at multiple wavelengths, and at this position, here, as multiple places. And in this figure, like we are subtracting this overall second-order dispersion, which can help you to better identify like what is really happening between the two resonators are coupling together. So as you can see here, we can have this at 1550, the first anomalous dispersion region we are pumping with, and also consequently the further anomalous dispersion regions we have. So next, I'm going to explain like why this coupling is like doesn't require any mode number matching. Like intuitively, it's not very strict, but kind of give you an idea like why this partial coupling doesn't require any mode number matching. An intuitive answer will be if you want to calculate the amount of coupling between two resonators, what you will be doing is in the calculation you will involve this integration, and this integration which involves the mode number of the two individual resonators. However, like this integration in this partial coupling case will only involve a fraction of their circumference instead of from 0 to 2 pi. So probably know like if you integrate from 0 to 2 pi, this integration will result as a delta function, which requires you have mode number matching in order to have a strong interaction between the two resonators. However, like if this integration doesn't involve 0 to 2 pi, like this will not be vanishing even if you don't have mode number matching with each other. So this kind of gives you an idea like why in our case this does not require mode number matching, and you will be able to have a spectral recurrence, and this spectral recurrence is set by the free spectral range difference between the two resonators. And in our case, we designed this free spectral range difference to be 0.5%, which means the periodic of this spectral recurrence is about 200 mode numbers. Okay, and as I just discussed, because we can have multiple anomalous dispersion regions, by pumping at one of them, it's possible for us to generate one pulse pair or one set of soliton comb. And by pumping at two of them simultaneously, it is possible for us to generate a multicolor soliton pulse pair simultaneously using the same device. And this experiment was demonstrated very quickly. And here's the resulted spectrum. And you can see like we have like two sets of optical frequency combs simultaneously generated from this resonator. And each of this optical frequency comb, soliton frequency comb features the well-known hyperbolic second square envelope at two distinct wavelengths. And the position of those two wavelengths can be arbitrarily designed by changing the length ratio or the recurrence period of the two resonator. Here's a quick demonstration. Any question? So sorry. Here is a quick demonstration of the verification of the coherence, and take a radio frequency beat note. You can see there are two strong, clean, single tone radio frequency beat note, and each of them corresponds to one of the soliton pulse pairs. We can discuss about how we can use this kind of soliton comb later, but let's first finishing our presentation very quick with the last point I'm going to discuss about. So I briefly introduced about this strong sideband earlier. I explained like why this sideband can be observed. The main reason is because the integrated dispersion of those sidebands is approximately the same with the pumping region. And this is called dispersive wave. And this phenomenon is also like earlier observed in very early studies of the on-chip soliton microcomb. As you can see in this experiment, the integrated dispersion is the same with the pump. At this position, you can have this strong dispersive wave as well. So in the next chart, I will try to explain like what is this integrated dispersion, and like what does it mean when you have like the same integrated dispersion with the pump. Hopefully this will be clear for you after this slide. So we start from the frequency domain. So in the frequency domain, the optical frequency comb features equally spaced comb lines, and the spacing between the comb lines is approximately the free spectral range of the resonator where you're pumping at. And here we assume that we are pumping at this comb is the comb that we are pumping at. And if you assign the mode number of comb orders to each individual comb lines, you can assign like this is the first order comb, second order comb lines, and etc. And again, so the distance between each individual comb lines are the same for optical frequency comb. However, the distance between adjacent optical mode of the resonator is not the same, because in the optical resonator, the media has a chromatic dispersion, so you don't have exactly the same distance between each individual resonator modes. So because of this mismatch, the frequency of the resonator will somehow walk off from the frequency of the comb. And here we assume this walk off is proportional to the second order dispersion. I'm missing a half here, but anyway, we assume like we are dominated by the second order dispersion. So this walk off will be proportional to the mode number of the resonator mode you are studying at. So for example, here we plot this as proportional to 1 squared. Here it's proportional to 2 squared. It's proportional to 3 squared, and etc. Typically, this walk-off is not comparable with the free spectral ranges, because in the integrated resonators, the free spectral ranges is typically very much larger than the fiber resonators, because the integrated resonators has a much smaller size. So typically, this walk-off is not comparable with much smaller than the free spectral ranges. However, like if your bandwidth is very large, and if this walk-off somehow gets comparable with the free spectral range, what will happen is that you can see here, when this is comparable or even equal to the free spectral range, at this position, you will finally get the resonator frequency and the comb frequency realigned with each other. And with this realignment, it's possible for you to generate a resonant enhancement of the power of the optical frequency comb at this position. So here is this resonant enhancement of the optical frequency comb power. We call this as a special type of dispersive wave, or Kelly sideband. This Kelly sideband is not very easy to be observed in the integrated photonic devices, as I just mentioned earlier, for a reason I just mentioned earlier. So, excuse me. I have about 5 minutes to go. Yeah, yes. So yeah. So go back to the integrated dispersion. So what the integration dispersion is doing, like we are plotting the number of this walk-off as a function of the mode number. So the first thing is that this integrated dispersion plot is scatter plot. It's not really a continuous plot. It's a scatter plot with the mode number it takes only integer numbers. And the amount of this walk-off is plotted as a function of the mode number, so that in our specific case, the amount of the walk-off is a parabola as shown here. And as you can see, like if somehow you get this the integrated dispersion the same or 0 again, what it means that you have the mode number, the mode gets realigned with the comb, and this resonant enhancement will create a dispersive wave I just discussed like 1 slide ago. And however, in our case, like we are having a walk-off that is comparable with the free spectral ranges, free spectral range. So in this case, like when the dispersive wave is, when the integrated dispersion is the same with the free spectral range, you will possibly be able to generate another kind of special dispersive wave, which is called Kelly sideband. And one other special property of the Kelly sideband is that you can see that the mode number between the comb and the mode actually is off by 1 in this specific case, which means that the phase of the Kelly sideband is actually have a 2 pi or integral of 2 pi off with the mode locked comb that you are emitting here. So which means that this phase mismatch needs to be somehow compensated in order to generate this kind of Kelly sideband, which is another reason like why this kind of Kelly sideband wasn't really observed before. So here are some historical review, but I'm going to go through this very quickly. So in order to generate this kind of Kelly sideband, you need to have some periodic perturbation, or in other words, somehow compensate that integral 2 pi phase mismatch between the comb and the Kelly sideband. So and the way that people do this is usually by introduce symmetry breaking. And for example, in this case, specifically, this is in the fiber, and they are doing is that they're periodically or they're splicing two segments of fibers with different dispersion scatter, so that you have like periodic perturbation, which can compensate the 2-pi phase mismatch. And in this case, like they have like a tapering design of the resonator, so that have a different periodic perturbation on the second order dispersion. And in this case, like they're pulse pumping it, and they can generate like multiple high orders of Chi sideband in this this kind of integrated. This is probably the only integrated photonic devices which can observe the Chi sideband we found in the literature. However, in our case, like we are generating this kind of Chi sideband, in our case with the interband nature. So we are pumping at one of the band, and this interband Chi sideband is generated on the other band. So you can see the generated Chi sideband at position 5 and position 4. They both like align with our theoretical prediction very well, because they appear at a position where the integrated dispersion is like 1 FSR away from your pump. And also, like this position can be actively tuned by changing the repetition rate of your comb, and because the repetition rate of your comb, if you pulse pump it, the repetition rate will be determined by the repetition rate of your input pulse. So this will be easier studied if you change the repetition rate. And if you increase the repetition rate a little bit, the position where the phase matching condition between the comb and the mode can happen will both shift towards longer wavelength side. And this is experimentally verified. By changing the repetition rate, you can see the position of the Chi sideband both move towards the longer wavelength side. Okay, so as I promised, this is concluding, but I'm not going to go through all the bullet points. I'm going to land at this animation where we started with. So hopefully after this presentation, I kind of can convince you that the optical frequency comb is a critical component that can connect between the frequencies within the radio frequency domain and the frequencies within the optical domain. So from one direction, from electronics to optics, like one critical application I just showed you is the optical frequency comb can be used for astronomical calibration, which is kind of you're taking the reliability and the stability of low phase noise of the radio frequency signal up to the optical frequency signal, and kind of use that for your interesting stuffs. And from the other side, from the other direction, from the optics to the electronics, I go through this very quickly, but hopefully you can notice that the optical frequency, the soliton frequency comb I discussed in the second part, is actually a kind of phase-locked optical frequency comb. And if you take the bit node between all the frequency comb, because their phase are the same, the bit node will have a single tone, clean, strong radio frequency signal. And by taking the bit node of the optical frequency comb, you can somehow down convert the stability of the optical domain, to the radio frequency domain. And this experiment is called optical frequency division, and credit to my colleagues, Xunxin. And this kind of optical frequency division can reach to a state of art phase noise as low as minus 155 dBc per hertz. And this is like a very promising path to move on for photonic engineering. There will be other further works I can talk about if questions raised there. And I would like to thank, there's a long list I can want to thank about that. Thank you so much for anyone here who being in my thesis event anyway. So yes, thank you so much for being here, and like this is the finale. Thank you so much. So like here's the open question time. So after the open session, we will have the closed door session. So any questions, please come now. And also for Zoom audiences, like you can send your questions to the chat in a Q&A session. And YouTube audience, you can also send your questions to the live chat. Yeah, please. You can kick in anytime, Charles.
Okay, I mean, this is Chaz. Yeah, thank you for a very nice presentation. I had one or two sort of general questions, and then maybe when we move into the smaller group,
okay,
one or two more technical ones. I mean, as you showed, the EO comb is a fairly bulky thing.
Mm-hmm.
What would you see as the eventual advantages of moving to the integrated photonic comb over the EO comb?
um, I think to answer your question, I guess probably you are more concerned with the real application for astronomical calibration. Um, in my I think in my naive thought, probably like why we land at the electro-optic frequency comb now is like in the astronomical calibration, we really care about reliability a lot because like you don't want something is done like in the middle of the observation night, right? So I think electro-optic comb is providing you a great advantage on that part. And by replacing the electro-optic comb with the more controlled, more like compact integrated frequency comb, I believe like this can give you advantage in let me think about this. This kind of can give you advantage in some other applications. Probably like different kind of combs have different good advantage in different areas, right? Probably like. Oh, yeah. That's a great point. Yeah. Yeah. That's a great point. Thank you so much for because like the real advantage for integrated photonic devices will be its compact size. So when the compact size really kicks in, that will be the great application that we can argue about the integrated photonic devices. Like for example, like as Carrie just mentioned, very appreciate that. As you can bring the frequency comb into a spacecraft. You don't want to bring a whole optical table into a spacecraft, but you can bring a compact frequency comb in the spacecraft. For example, you can do something interesting, exciting in the space. That probably is an example for this specific astronomy application. Mhm. For astronomers.
Yeah, okay, thank you. I mean, I was just thinking also that you just start to get rid of more components.
Mhm.
As you get more chip-based photonic integration, you can start imagining a system where the seed comb is on a chip. You can imagine a spectral flattener on a chip. So I'm just trying to see the eventual evolution of what is a very complicated, large, power hungry
Oh, that's a
system into
yeah.
something smaller, more compact, lower power.
Yeah, exactly. That's a. I think the only difficulty for those arguments is that needs time, right? It probably doesn't sound realistic now, but I believe that there will be sometime reliable, like later, like probably 10, 20 years ago, 20 years later. Right? Probably don't the only drawback I can answer Irida's question probably is it's not reliable now, but only now, and you don't know what will happen like 20 years later, and I believe like it will happen very fast. And what I was thinking like when I was thinking about Charles' question just now is that microcomb probably is not very good for absolute frequency referencing for now because like we need to log FCO of the microcomb as well for astronomers. But for now, like probably that's not very reliable yet. But we really don't know what happens in 20 years. So.
Okay, then that's the other more general question would be just building on what I asked earlier is, I mean, what are the prospects for pushing, either technology, either the EO combs or the microresonators down towards shorter wavelengths? What are sort of the fundamental, say, material limitations, and how could we perhaps get around them?
Let me make sure like I understood your question clearly. So you were thinking about like making a integrated frequency comb at a shorter wavelength, for example, visible.
Yeah, or even EO comb. I mean, all this is done the telecom bands,
Uh-huh.
because for very good reasons.
Uh-huh.
But I think there's lots of utility for having these sort of combs operating down at shorter wavelengths.
Uh-huh.
What are some of the limitations that make that difficult?
Okay. We can answer this in two perspectives, I think. So first, you can argue some technical difficulty may have for electro-optical combs itself. For electro-optical combs, people, I believe that there was some previous work try to develop a 780 electro-optical frequency comb there, but I think that kind of we concluded it's kind of hard due to some instrumental limit, because like you need to have like really good amplifier, for example, at 780. You need to have uh-huh, yeah.
I mean, kind of related to this question,
Mhm.
the previous question. I mean, in my mind, the big differences right now are for electro-optic versus microcombs,
Mhm.
is that you can build an electro-optic comb using commercial
Oh,
off-the-shelf components.
oh, that's also
Rather than really certified and qualified by telecom.
that's also a reason. Yeah.
You can't do that.
Yeah.
And I think as this other question, as you go to invisible, there are choices, there are commercial off-the-shelf choices for modulators. But it does it's just the difficulty of using them
Mhm.
increases because
Yeah.
there are fewer choices relative to.
Oh, yeah. That's
Yeah. So I mean, it's kind of like it's commercial availability versus
reliability.
laboratory grade
Yeah.
devices.
Yeah. So yeah, if you answer this question in the perspective view from the electro-optics frequency cone, it's mainly because like what is commercially reliable, like do we have any choices, like would you have like any more reliable components or substitutes you can have at 780, and how does a modulator perform at 780, etc., etc. But those are like not related with science probably,
Yeah,
but
let's ask the same question though, but specific to solid-time microcomb, pushing it visible.
yeah.
What are the challenges there?
So if you exactly, that's the second part I was trying to talk about. So if you want to push the solid-time microcomb to the visible, the main challenge, the other part was the solid-time microcomb. If you want to push that to the visible, main challenge would be dispersion, because like the dispersion I just mentioned about it, almost all the material have normal dispersion in the visible band. So probably that's the main reason like why this was so hard before, to generate the solid-time microcomb in any other materials. But importantly, however, like with the dispersion engineering technique we proposed using the multiple resonators that are coupled together, it's kind of like we can arbitrarily change what kind of dispersion we want. And there were some recent demonstrations in secret by my colleague groups that we have demonstrated somehow like close to visible solid-time microcomb generated from the coupled ring resonators. So yeah, so I believe like those are very promising in the future. And I really expect sometimes I can see those things be applied in astronomy applications in the future.
Thank you.
Yeah, thank you.
By taking your 1500 and triple the frequency.
Oh, that's a great question. So let me repeat Paul's question. And also make sure I understood it clearly. So like Paul just asked if we can generate a visible solid-time frequency comb by taking the multiple harmonics from the 1550 and use that as a pump to generate a solid-time microcomb. Is that the kind of question?
Just get the third harmonic of the whole thing.
I believe that is possible. I believe because like we have third order nonlinearity in the silicon nitride, and that depends on like what you are thinking about. Like, if you are thinking about harmonic getting a third harmonic of the full comb down to the 3F region, that's gonna be hard because it's hard for you to get phase matching conditions to do this 3F generation in the resonator for the full bandwidth. That's gonna be hard. But if you think about generating a 3F first in the silicon nitride and then generating the cascaded frequency comb as visible, I would say that that's possible in principle scientifically, but just what I'll be worrying about is the strength of the third harmonic, right? So and how you're going to get that phase matching to be reliable.
In stages maybe, but.
Yeah.
But, I mean, if you don't care about efficiency,
Mhm.
and you just want the wavelengths, you could do that.
Yeah. I agree with you. Yes. Okay. Yes. Thank you so much for everyone, and I will stop the YouTube and also the of course, and also like I invite everyone in the Zoom exit the Zoom room now, because we're going to enter the closed door session.
Chaz, can you hear us? Is this working? I think we thought it was working. Works in the room, but I guess it doesn't really work on the Zoom.
Maybe you can try to put the microphone closer. Maybe.
Is this really? Is this connected to?
I think that is connected as well, and you could speak. Charles, can you hear the voice from the other committee members?
Not very well. I hear you very, very well, but not the audience.
Let me try to use the audio from my side. Okay. Try to mute.
Yeah, there's a lot of echo that way. Maybe it's just best to share the microphone and go back to the other way.
Are there any? Oh.
Yeah, I think you're still muted.
Am I clear now?
I can hear you fine. So maybe just share the microphone with
Sure. We will share the microphone.
the
Yeah.
audience.
Sure. Right.
Okay.
Thank you. Yeah.
So now we can. Nobody else is on Zoom.
Nobody else. Yeah.
Okay, so we can start asking questions. Chaz, you want to go first now that you're on Zoom?
Yeah, sure. I mean, one of the challenges, this is sort of a more technical one about the Keck system and the Parvy system, Palomar system before it, is one of the challenges we had is shaping the pulse properly, to get a comb that eventually had a good bandwidth. Can you
Right.
talk a little bit more about why the pulse shape is so important, and then what are the techniques we use to optimize the pulse shape?
Oh, thank you so much for the question. Oh, excuse me. Oh yeah, excuse me. So I need to, I need to stop the YouTube as well. So sorry, Charles. Give me 1 second.